In the last video, we saw the idea of direct addressing. The idea here was basically that we would set the index in the array for our data to be the same as the ID for that data. With the idea being that if we have the ID of the data, we can then find all of the data associated with it using a constant time lookup, since we can index to a list in constant time. This approach worked very well, however, it has some drawbacks to it. The main drawback was that data may not be sequential. So we may not have IDs in sequential order. We may have, ID 0, ID 1000, ID 101. And if we were to store that inside of a list, we would have all of this empty space around those values. So we would be wasting some memory space, which isn't really ideal. The other problem is that as the number of IDs grows very large, we may not have enough space to actually store that inside of a list, or it may start to get a bit more expensive to actually store that data. So we want to try to solve these two problems, right? We want to reduce the amount of IDs that are possibly available. And then we also want to try to make the data more uniformly distributed. And the main approach to doing this is going to be using a hash function. A hash function is a type of mathematical function that can generate a fixed size output for any input. This property makes it easier for us to control the size of our actual hash table itself. And additionally, typically a hash function is going to be more uniformly distributed with its data. When we add data into it, it's going to have a more uniform distribution of data throughout our list. Now, I'm just going to go ahead and say here that the idea of hashing functions can get very complex very quickly. For that matter, for most of our actual uses of hash tables, we're going to opt to use built-in hash tables. So Python's built-in hash tables a dictionary. We'll talk about that a little bit later. So the ones that I'm going to show you here are going to be very simplistic examples. If you want to dive more into the complex ideas that we use for, production level hash tables, you can read a bit more about how Python's dictionary is implemented. We'll talk a little bit about that in detail in this course, but those sorts of details you can learn a bit more about to get a more full picture around it. But I just want to get you more of that intuition around it and then show you how we can actually use the hash tables themselves. So let's talk about one approach that we can use for a hash function. A pretty common idea is the idea of the modulus operator. So if you've forgotten about the modulus operator, it's represented by this %sign. Basically what it tells you is it tells you the remainder from division. So if I were to say that my function was h of x equals x modulus a, basically it would tell me the remainder of x divided by a, right? So that's the idea of our modulus operator. The modulus operator works really nicely for a few different reasons. The first reason is that if the value a that we're using is a prime number, we can guarantee that all of the values starting at 0 up to a produce a unique output. That is because no number is going to divide a prime number except for itself in 0. So all the other numbers up to that point are going to have a unique remainder from division. After a, they start repeating again, right? And that's actually another nice feature of the modulus operator. It's what people often refer to it as like a clock-based arithmetic. When you reach the value a, the values start repeating themselves again, and they kind of go cyclic like this, right? So if a were to be 5, for instance, basically all the remainders from 0 up to 5 would be unique. And then after that, they start repeating each other. So you get this like 0, 1, 2, 3, 4, 5, and then 0, 1, 2, 3, 4, 5. And they just keep repeating like that over and over. So it actually reduces down the number of possible outputs. No matter what IDs we put into this, we're always going to get a value from 0 to 5. So we know exactly what sort of values we're going to be getting as a result from this modulus operator. So this is a very helpful way for us to be able to control the actual input and output sizes. So then what are the downsides of this? Well, the main downside is actually that it repeats, right? So the fact that it repeats is both a benefit and a downside. The reason why it's a downside is because you can imagine if you store a value that, say gives you us a value of 1 as an output, right? If we then store another value that happens to have 1 as an output, both of those values would be in the same spot in our array. We call that a collision. And there's a lot of different ways that we could approach solving for a collision. We'll discuss those in more detail as we continue on through our hash table implementation. So just keep that in mind that we do have that small little problem there. But for now, we'll just do our implementation, and then we'll talk about solving that problem a bit later on. So the way that our hash table ends up looking is going to be something like this. I'll take this away, and I'll place these users down a bit, and I'll create my class for my hash table. And basically we have our initialization, And we want to create two things. I'm going to create my table, which is going to be initialized to a bunch of null values. And the number of null values I want are going to be the same as the modulus value, which I'll allow people to provide to the hash table as an argument. And then generally, I'll just keep track of the modulus value that was provided. So basically, when you initialize this, you tell the hash table which modulus you want to actually be using. So if I wanted to do mod 5, I could do 5 as an argument, and it would initialize it with 5 empty spaces for us to use, and it would use 5 for all of its modulus operations, right? So that would be an example of using this. Now, in order to insert values into this hash table, we need to provide an ID and a value. And what happens is it's going to take the hash table, and it's going to store at the location ID mod self.mod the value, right? So for example, if I have the user with an ID of 1, and they have some data associated with them, well, actually, I'll just show you what happens, right? So if I have the user, say, 0, and I want to store it as in my hash table, I could do h.insert at the ID 0, the value a, right? A being the user that we want to store in this case. And I would have to place these actually above this so that I can use the reference. There we go. And then if I were to print to you the actual hash table itself, you'll see exactly what happens, right? So let me show you here. So we'll do, I have it in chapter 6, hash table.py. Do you see that this gets stored in index 0? Because 0 mod 5 gives us the value 0, right? And then similarly, if I were to insert, say, ID 1 for value b, right, since it has an ID of 1, we'll see that this gets stored at index 1. Since 1 mod 5 equals 1. Now, these examples may not be, as interesting because, the IDs are basically matching in this case. But suppose that I gave this person the ID of 8, right? Take a look at what happens when I insert the value 8 into this hash table. What ends up happening is that value actually gets placed right here, right? And the index that is 0, 1, 2, 3. It's at index 3. So do you see that the value 8 as an ID got changed to be index 3? That's because 8 mod 5 is equal to 3, so that's the ID that it got mapped to. So do you see how that mapping is generally working, right? That helps to understand a bit more about how this is actually getting mapped through, right? So that's how this insert is generally working. Like I say, this operation here is constant time, this operation here is constant time, so we can actually insert still in a constant time, right? Now, in terms of our get, to get a value out of this hash table, well, we just return self.hashtable at ID mod self.mod, right? So if I want to get the value 8, it just returns me 8 mod 5, which would be index 3. So it gives me back the same value. Do you see how that generally is going to work to give us the values as well as set them properly, right? This is also constant time, so we can get in constant time, we can insert in constant time, everything's great. One final application of a hash table, which is a very important one, is that we could check if it contains a value in constant time. And the way that we do this is just as follows. We could say contains, and if we provide to it the ID, we just return self.hashtable at ID mod self.mod equals none, right? So we could just check to see if the value is none or not. If the value is none, then it's not in the hash table. If the value is not none, then it must be in the hash table, right? So you can see that here, if I do h.contains 8, right, we should get a value of true since that value is inside of the hash table, right? And we see here that, oh, in this case, it's giving me the value of false. I think that's just because in Python, I just have to say is none, like this, right? Or rather, is not none, right? Because it would be the value is not none to check to see if it's actually contained. So then from here, we could just say does not equal none, right? So there we go. Yeah. So now it's does not equal none, sorry, because that would be checking to see if an actual value is there, right? The way that I had it before, we were basically checking to see if the value was not there, right? So this is the opposite of it. So we can see that 8 returns true because that value is inside of our hash table. However, if I did 9, for example, that value is not in the hash table. So you can see that we can check that, and we can check that in constant time. So this is a fantastic approach. And generally, if I make the modulus value large enough, right, I can avoid any sort of collisions between our values. So I can avoid two values hashing to the same ID value, creating that collision. However, because of the fact that we want to contain our values relatively inside of a small space, collision is often inevitable. We're going to have some form of collision at some point. So we ought to talk a little bit about the ideas of solving for collisions. So in the next few videos, I'm going to talk to you about a few different approaches for solving collisions. And then we'll take a look at some practice problems that we can do with our hash tables. So thanks so much for watching this video. I'll see you in the next one.